Hello everyone. In this video I'll be talking with you about the energy of a capacitor, and what I'll be doing is I'll be deriving the expression that we see in textbooks here. And so to start with, the energy of the capacitor, which is Wc of T, that is work of capacitor with time as a time function. Actually, the capacitor doesn't dissipate any of this energy. What it actually does is just store it. So it's the associated energy of the capacitor, what it handles. And so we'll start with power. Power, Pc of T, is going to be equal to dWc of T dt. Next, we'll take notice of the fact, just Ohm's law, voltage times current equals power. It gives you power. So we have Vc of T times Ic of T is equal to power as well. And so we have generally basically laid out our equation that we'll be working with here. Now, what we're going to do next is we're going to take this power and put it in terms of Vc of T itself. And so we have Ic of T equal C dVc of T dt. And we're going to use that as a substitution in here, and it'll be in terms of Vc of T. So now that gives us Pc of T equals dWc of T dt equals Vc of T, and now we have C dVc of T dt. Next, what we'll do is we will multiply by dt, and effectively that gives us Pc of T dt equals dWc of T, which equals, and we'll bring the C out, the capacitance value C in front, and so now we have C times Vc of T dVc of T. Next, what we'll do is we'll go ahead and we'll try and start to integrate this, taking note of the fact that when we have just power in general, when we integrate that across two limits, say T1 and T2, so the graph would look like this. In time, we'd have T1 and T2, and this is power. If this was a measure of power there, what's under that graph would be energy. So that equals energy, and then we will form some integration limits there. So next what we'll do is we'll go ahead and set up our integration, Pc of T dt, integration here, dWc of T equals C integration Vc of T dVc of T. Now next, for our integration limits, what I'll do is I will use some substitution here, some very basic substitution, in order to free up what we want our integration. Once we apply it and we evaluate it, we want it to be in terms of the variables that we have here. So we're going to use some substitution. And so I'm going to call, first of all, over here we have dt, so t is the integration variable, and we'll substitute that. I'll give it arbitrary variable substitution as alpha. Over here we have dWc of t, so Wc of t I'll make equal to beta. Over here we have dVc of t, so I'll make Vc of t equal to just any variable that you can think of. I'll call it A. And so now we can actually set up some integration limits in terms of what we want to recover here. And so now the very next step, make some room here. Now we have over on our left hand side T, and let's make our, instead of using T1, we'll use T sub 0. and we have PC of alpha, because remember we just replaced PC of alpha d alpha equals between WC of t, WC of t sub 0, d instead of WC of t, d beta, and that's going to be equal to C and times VC of t and VC of t sub 0 as our integration limits, and then VC of t are going to substitute. We have A, and then again here we have dA instead of dVC of t. And so now we have our integration set up, and make some more room here. And so next we have, I'll restate this here, between t and t sub 0, PC of alpha d alpha equals WC of t. Well, actually I might as well just go ahead and start integration. That's the very next step. And so now we have beta to the first power over 1, and that just gives us simply beta. That's between WC of t, WC of t sub 0, and we have C over here being multiplied by a to the second power over 2, evaluated between the limits of VC of t and VC of t sub 0. Next, we have t sub 0, PC of alpha, d alpha equal WC of t minus WC of t sub 0, and here we have C times VC of t squared over 2 minus VC of t sub 0 squared over 2. And so next what we'll take notice of is that we can reduce this a bit due to the fact that usually the energy of the capacitor at time equals 0 is usually 0 at that given point. Usually what they do is they bring that out and they say that that's 0, so it simplifies things, and that corresponds to our C times negative VC of t sub 0 squared over 2 over here. So this term is zeroed out as well because you have a direct correspondence. And so next, ultimately, what we have is our final form is our power over here being integrated between t and t sub 0, d alpha equal WC of t, which equals C times VC of t squared over 2. And so this is our final formula that we have, and this is how we come about that in textbooks. Of course, you bring the 2 out in front here, and then that'll be a half, times C times VC of t squared. And so this is how we can derive this formula here, and that pretty much does it for this derivation of this function. Hopefully this video was helpful for you. Thank you for watching, and have a nice day.